I've been in networking for over a decade and decided to make some content to try to help others understand this industry.
Let's talk about what private IP addresses are and why we have them. The world population in 2025 was estimated to be about 8.2 billion people. In 2023, there was an average of 3.6 devices per person in the world, and these would be internet connected devices. So if we multiply that out with 8.2 billion people and 3.6 devices per person, that would mean there's 29.5 billion internet connected devices. Now, since an IPv4 address is 32 bits long, that means that there's a finite number of addresses or unique values that we can have. And we can figure out what that is by taking 2 to the power of 32. When we multiply that out, we get about 4.3 ish billion unique addresses. So if we have 29.5 billion devices that need to be connected to the network, and we only have 4.3 billion unique addresses, we're off by about 25 billion addresses or 25 billion devices that need connectivity to the internet that we can't support and give a unique IP to. The Internet Engineering Task Force, or IETF, they predicted that we would reach a point where there would be more devices than IP addresses, so something needed to be done. And their solution to that came in 1996. The IETF ratified RFC 1918, which solves the issue of address exhaustion. So in RFC 1918, it defines these three addresses or networks as being private IP addresses. These addresses are not routable across the internet, and an internet service provider will drop any packets that have these IPs on them because these cannot be routed across the internet. These are private only. By itself, it seems a little counterintuitive that if we're running out of IP addresses, then why did we just take a bunch of IP addresses and say these are no longer routable across the internet? How does that fix the issue? Well, another feature that came out is called network address translation, or NAT. And NAT can be used along with these private IP addresses to expand the number of devices that IPv4 can support. And it allows the reuse of these private IP addresses. And here's how it works. So let's say I have a PC that has an IP address of 192.168.1.1. That is part of the RFC 1918 space, so this is a private IP address that cannot be routed across the internet. So I connect that host to a router, and that router is then connected to the internet or my internet service provider. So the router receives a public IP address from the internet service provider. In this example, we'll say it's 1.2.3.4. That is a perfectly valid public IP address. So let's say that my host is trying to ping another device that's out on the internet, and it has an IP address of 8.8.8.8. So when traffic from the PC is sent to the router, it will have a layer 3 source IP address of 192.168.1.1, since that is the IP address of the PC. And it'll have a destination IP address of 8.8.8.8. Our PC sends that up to the router. And if the router were to send this out exactly as it is, it would get dropped by the internet service provider. So the router has to make the traffic acceptable for the internet service provider. So it replaces the private IP address and it puts its public IP address in its place as the source. So now the source IP address is 1.2.3.4. But the router can't just do this and forget about it. It has to remember that it did this substitution or this translation. So it has a translations table and it puts that entry in there, remembering that it used, when it saw a source IP address of 192.168.1.1, it translated that to 1.2.3.4. So now when that packet is sent out to the internet service provider sees only public IP addresses on it, and it will forward that traffic as normal. This is perfectly legal, valid to have as a public packet. So the packet will eventually reach its destination of 8.8.8.8, and the destination sees that the source that is communicated to it is 1.2.3.4. Looks at the destination, sees that it is itself, knows that it is the destination, processes the rest of the layers up through layer 7. And if the 8.8.8.8 device has to respond, when it sends a reply, it's going to craft its packet to have a layer 3 header of a source IP address of 8.8.8.8, which is itself. And it's going to have a destination IP address of 1.2.3.4 because that's what that host saw as the original source. So now these are both public IP addresses again. We can see that. So the host will then send that to the internet, and public IP addresses as source and destinations here, so no issues from the internet service provider side of things, and it forwards it to the router that has the IP address of 1.2.3.4. And when the router receives the reply, it looks in its translations table and it sees that 1.2.3.4 it was originally the private IP address of 192.168.1.1. The router now replaces that layer 3 destination address that was 1.2.3.4 with the original 192.168.1.1. So now this packet looks like what the PC would be expecting as a reply. So when the router sends that to the PC sees that the destination IP address is 192.168.1.1, which is its own IP address, and it knows it's reached its layer 3 destination and processes the rest of the packet. So how does this help with IP address exhaustion, just doing this translation? So let's go back to what we looked at originally, how we had 4.3 billion unique IP addresses for IPv4, but we have 29.5 billion devices and growing. Keep that in mind. So the RFC 1918, if we were to take how many addresses that were designated as private IP addresses in RFC 1918, we would get about 18 million addresses that are now removed from that public pool and they're in this private pool. So that leaves us with roughly 4.27 billion IP addresses. Now, theoretically, there can be tens of thousands of private IP addresses behind each one of these public IP addresses. There can be more than 10,000. So we'll just say 10,000 for the sake of it, because not every single public IP address will have private IP addresses behind it, and not every network that uses private IP addresses is going to have 10,000 devices behind it or 65,000. Yeah. So we'll just say 10,000. And if we multiply that 4.2 billion remaining public IP addresses by our roughly 10,000 private IP addresses that can be natted behind each public IP, we can see that we get about 42.7 trillion IP addresses that are now available for IPv4 use. So the combination of private IP addressing and network address translation, this significantly extends the address pool for IPv4 and also extends the lifetime of that protocol so that we don't have to move to IPv6. So we went from being able to support about 4.3 billion devices originally with IPv4 to now we can support over 40 trillion devices just by using private IP addresses and network address translation.